Good, good morning, good evening, and good afternoon, everyone. Today, I will be the moderator of this keynote, and let's welcome our keynote speaker, Professor Liu Gang. I will give a brief introduction about Professor Liu and his topic today. So our keynote will be on the topic about digitalization, urban built environment stock for circular and low carbon transition of cities. And Professor Liu has been the professor of industrial ecology at the University of Southern Denmark and is now the chair professor at Peking University. His research interests concern mapping and informing the circular, low carbon, and just transition of resources, industry, and urban systems. His work has been published widely in high-profile journals such as Nature Climate Change, Nature Food, and Nature Communication. He has been awarded the Robert A. Loudis Medal by the International Society for Industrial Ecology and the James J. Morgan Early Career Award by Environmental Science and Technology, and the Best Research for Digital Built Environment by the World of Digital Built Environment. So let's welcome Professor Liu.
Okay, thanks a lot for the introduction. You can hear me well? I will put on my slides as well. I think you can see my screen as well, right?
Yes, it's very clear.
Okay. I will switch off my camera when I'm speaking, but in a Q&A, I will turn it on just for the sake of the internet speed. So, yeah, as the moderator introduced, what I will do in the next 40 minutes or so is to share with you our work on digitalizing urban built environment stocks for circular and low carbon transition of cities. I will try my best to keep within 40 minutes, so we will have time for discussion or Q&A if you have any. Well, first, I think this is a kind of all know when we talk about accessibility transitions or accessibility challenges. So we will win or lose our battle against accessibility challenges in cities. I mean, if you look at this very widely used imageries for nighttime light from NASA, you will see, of course, a lot of nighttime light will be only seen in urbanized areas, for example, in Europe, in North America, but also in East Asia. If you look at those statistics, no matter what kind of statistics or what kind of accessibility challenges we talk about, energy consumption, greenhouse gas emissions, raw material consumption, cities together in the world, they take up almost 3/4 or 45 to 80% of all these resource and environmental challenges. Of course, cities also host roughly 70% of people in the world, and this, of course, is expected to increase further as more and more people will move into cities in Asia, Africa, and South America. So how can we address these kind of issues? There will be, there are different tools and methods from different disciplines. What we have done and offer is a kind of a metaphor we borrow from ecology. So when you look at a city, how a city developed, for example, here, a city, developed around kind of a settlement around a river and further expand to a mega city. It looks pretty much the same as if we look at a cell growth or a human being growth. So first, it has a life. So we will generate impact, during the lifetime of cities, not only for the build-up, so we will construct buildings, the infrastructure, but also generate impacts during the operation, for not only constructing the buildings, but also, to heat up the buildings and also to cook, for example. And also we generate impacts at the end of life when we demolish the buildings. So this is sometimes we call a physical economy. So this is the same as we generate all kind of impacts during the lifespan of a human or of a cell. Secondly, it has a metabolism. So like a cell, we have catabolism and anabolism. So that means we will consume energy and resource, and at the same time, we generate waste and emissions. And such a cell or such a person will, of course, then also provide a kind of service. So these kind of metabolism for cities are very important because these are the drivers, for all the energy use and emissions and waste generation, as we have shown in the previous slide. If you look at comparison in a diagram here, for a prehistoric person and a modern family. So for prehistoric person, so of course we still consume some. There was an inflow in terms of food and water, and we generated some sort of waste. But we had almost nothing as stock, so even probably without proper clothes. But for a modern family or a modern family in a modern city, so we have much larger consumption, of course. We not only need food and water, but also we need construction materials, and we generate different types of waste. And also we have a lot of stocks in terms of buildings, vehicles, infrastructure, consumer goods. So all this kind of product and infrastructure provide essential services for cities. So that means city has a weight as well. And this is very important because such a weight factor provides spatial and temporal lock-ins for all the sustainability challenges we will address. For spatial lock-in, I think that's very straightforward. For buildings and infrastructure, once we have constructed them, they will not be movable. So that defines also, for example, our demand for transportation and other kind of urban services. For temporal lock-in, that's also straightforward. So, for example, once we have a building, no matter if it is energy efficient or inefficient, it defines, the basic conditions for the energy consumption. For example, if you have a certain energy label for such a building, and that will last for a lifespan of buildings, if it is 50 years or 80 years and so on. So this kind of system delays are also very important and provide such kind of a background for the urban sustainability challenges. So based on this kind of understanding, we use a so-called social metabolic analytics approach. So to put it very simple, we can look at such a city as a metabolic process, as I mentioned, for the resource consumption, but also for waste generation. And we can characterize this from two perspectives. One is from a telescope perspective, and one is from microscope perspective. By telescope, I mean, we have statistics, we have economics, we have all kind of top-down, way of data generation, and also analysis. By microscope, I mean, for all engineering knowledge and also bottom-up information we can collect, that's also important for such issues. In addition, we have another perspective for the metabolism, as I mentioned already. So that means we will consume energy, water, and materials, and generate greenhouse gas emissions, heat loss, wastewater, solid waste, and we have to consider both anabolism and catabolism. Adding more complexity to this is, cities are also very much interlinked with their hinterland, but also among themselves. So there are trade and exchange links among cities and between city and the hinterland. So that means we will have actually increasing importance of international trade or exchange across these regions, across these cities. So by putting different elements together, from a physical point of view, to characterize the stocks and flows across or throughout the cities. We call this a social metabolic analytical way. And this is important because it provides basic understanding for fine management with high spatial, temporal, and technology resolution. As I mentioned already, when we understand urban stocks and flows with a high resolution, it also provides a life cycle management perspective, considering both upstream, the very current debate in the climate policy, especially for cities, is this so-called embodied carbon for both construction sector and cities. So we consider that as well in the upstream, but also the downstream, including, of course, operation of the buildings, but also the end-of-life management. It also provides a basis for managing the nexus among resources, for example, water, energy, and materials. There has been also a lot of discussion in the past years around food, water, energy nexus, and also nexus between resource, energy, and environmental systems. It also helps address these security issues when we look at the entire supply chain. So when we characterize all these flows, so here's just one example, or two examples actually, when we characterize the flows within these cities from such a metabolic perspective. For on the left, Brussels in the early 1970s, and on the right, more recent characterization for the major Danish cities. If you look at the figure on the left, this was of course a bit like outdated, but you can still see they can characterize flows in terms of greenhouse or carbon dioxide. And that time, of course, climate change was not a major issue yet, but we could still balance all these outflows and inflows, for example, fossil fuel combustion, import, export, the energy consumption, and so on. So this, of course, provides a physical description of how we use resources, energy, and how much waste we generate as a result of such consumption activities. On the right here, we characterize the inflows and outflows for 4 major Danish cities, Copenhagen and 3 other Danish cities. So here you see, the 4 cities, we characterize, water use, energy use, food consumption, greenhouse gas emissions, solid waste generation, construction demolition waste generation, and municipal solid waste generation. So here for each city, we characterize the share of that city out of the national total in terms of population, but also in terms of energy consumption, waste, different types of waste generation, and so on. So you will see, of course, there is a scale economy. So that means, for example, if you look at, let's see, Copenhagen as a case. So, the share of population is very high. It's almost 10% of people in Denmark live in one single city, the capital, Copenhagen. But the per capita or the total, the share of the total resource consumption and waste generation is much lower. So this means the scale of economy does help, reduce the total energy use and emissions and so on. So such kind of flow understanding for the urban metabolism is very important for supporting urban sustainability challenges, including the circular economy and climate change mitigation, as I put in the title. However, only looking at these flows is not sufficient or is not enough, because if we characterize our built environment as a tree, actually most of the flows are depending on the scale, the quantity, and the quality of the stocks. For example, how much water we consume, of course, depends on also the floor areas of buildings, the industrial capacity, and so on. So these kind of stocks are very important because they provide the services to us. Buildings provide, shelter and service, transport infrastructure provide mobility service, and so on. So they are also, the physical backbone of our cities, in terms of buildings, different types of infrastructure. They also couple the consumption in the upstream and in the downstream, as I mentioned already. And they also define the city, the urban fabrics in a physical way. And also they provide temporal dynamic or temporal lock-in, as I mentioned before. So it is a kind of a dynamic determiner. And most importantly, this built environment also serves as a resource repository. So that means once we consume a resource, in cities, most of them will be put into those stocks for quite long. If we talk about vehicles, maybe 16 years. If we talk about buildings, maybe 80 years. So they will stay there very long. And understanding these stocks is very important. Here I give one example from a top-down perspective. So these are not for cities, but rather on the country level. But you can see here we visualize how aluminum has been accumulated, not only underground. Of course, when we talk about underground, that is, reserve, right? So aluminum equivalent in bauxite. So these graphs shows, basically, the bauxite reserve underground, basically in those countries where you have mines, Australia, Brazil, and Guinea. More interesting is aluminum stocks above ground. So these are aluminum stocks accumulated in our products and built environment. So after over 150 years, because aluminum was first commercially or industrially produced since 1870. So over 150 years, we have been digging out bauxite, put them into the society as aluminum in different products. And of course, there will be maintenance and also replacement for these products. So this graph shows how we have been accumulating aluminum in our society. Oh, by the way, the size of a country are proportional to the total stock, and the color scale here indicates the per capita value. So you will see, if we talk about aluminum stocks above ground, it will be different because most of them, has been accumulated in the major economies, North America, Europe, and China. On a per capita scale, however, you will see the major industrialized countries like USA, Germany, and so on, they have much higher value, over, for example, 600 kilogram per capita, to enjoy the current service of life. While developing countries like China and other developing countries have much lower value. So the global average in 2009, this was a bit old data, was 90 kilogram per capita. So these kind of stocks not only define the future recycling potentials, because these stocks are basically so-called urban mines, they also define the future demand, because as we expect further urbanization in East Asia, in Africa and South America, we will see more and more vehicles, buildings, and urban services in these continents. So that means we will be also accumulating more metals in these stocks. So this tells us we of course want a more circular economy, because we want to focus on the flow side, like I showed for the Brussels case and Danish case. So we want to get back, for example, the municipal solid waste, no matter if it is incineration, composting, or whatever. We also want to address the stock. So here is a visualization in which we plot the cement stocks on a per capita level against the urbanization rate measured as percentage of urban residents in total population. So you will see in major industrialized economies like UK, US, France, Germany, when they reached the urbanization rate of 80%, so 80% people living in cities in those countries, they have roughly per capita cement stock of 20 tons per capita. So for each Japanese, for example, to enjoy the current service or lifestyle, they have to carry 20 tons of cement on their back in order to have the buildings, infrastructure, and so on. There are a few exceptions. You see, well, Japan, there's a very post-war construction boom, so the stock curve is very steep. This is not very often seen, because stock curve is often more smooth, as it's accumulation of the resource, right? And also for Brazil, you see Brazil has already a very high urbanization rate in terms of people living in cities. So this matches for their urbanization mode. So you will see, or if you think about cities in like Sao Paulo or Rio, so a lot of people live in the slums. They live in cities already, but they do not necessarily have the services provided by buildings and infrastructure. China is even more exceptional. So you see, China just reached the level of 60% people living in cities. It has already a high per capita cement stock, like 20 tons per capita. There are, of course, some reasons we can dig out. For example, the infrastructure investment in the past decade or decades, like Three Gorge Dam, the high-speed rail, also a construction bubble. So this is kind of the opposite, comparing to Brazil. So buildings are constructed already there, and then people, do not choose to live there or cannot afford to buy them yet. I mean, here is a very famous case, Ordos in Inner Mongolia. If some of you heard about it, could also be production overestimation or a combination of these factors. For bulk materials or construction materials in cities like cement, it is not a major issue, for how much we consume. It is actually, the number is actually quite astonishing. So here is a comparison made famous by Bill Gates. He wrote a book review for a book he has read. I mean, this was correct. So this was a very old number actually already. Between 2010 and 2012, 3 years, China used almost the same or even more cement than the US did in the entire 20th century. So this is not comparing China with Denmark. It's the top, 2 world major economies. China used the same amount of cement in 3 years that the United States used in the entire, 20th century. Well, again, this is not probably a resource issue, so we will be able to find enough resource to produce the cement, but it might, be a challenge for the waste management, for example, in the future, or for the greenhouse gas emissions, because we know cement production is very emission intensive. So that will be the challenges we will face, for the circular and low carbon transition for cities. So I call this, it might be the unbearable weight of the Chinese urban dream. So we have to look at why this number is so high. But a better understanding of these patterns and drivers requires really a high or higher resolution characterization of the urban building environment stocks. So comparing to what I have shown on the national scale and also using top down, we need a higher resolution. Well, here, when we have such information, we could also combine such stocks and flows information for the as I said, low carbon urban development discussion. So here we link the different types of urban stocks and flows with different greenhouse gas emission accounting scope, both scope 1, 2, and 3. So we not only look at the major economic sectors, but also we look into the different types of stocks. For example, when we talk about building emissions, we look at the buildings in the household. That means our residential building, but also buildings in the public sector and in the private sector, and also some buildings in the transport sector. We can link also different types of stocks and flows, because here this is for a case of a Danish city. We have a relatively higher resolution on the stocks and flows and their interaction. But here we still only provide the aggregate number. We do not zoom in for the spatial and temporal perspective. As we talked about, this kind of spatial temporal lock-in is very important to be considered when we talk about this urban transition. So how can we do that? I think in the past years, the new types of data really open a new window, because the previous figures and characterization on a global scale I showed are pretty much based on statistics and modeling and industrial ecology or engineering system types of modeling. if we want to zoom in and to have a higher resolution, we have to rely on the increasing availability and amount of new types of data. So here I show a few examples. So satellite images, remote sensing, land use and net cover change, nighttime night imageries, and so on and so forth. But also increasing amount of big geodata like point of interest, the vehicle travel patterns, different types of sensor data, and so on. But also, within the construction sector, this kind of digitalization trend, provides also a lot of data for this kind of analysis, like from architectural or the BIMS data, the building information management system. So that's something we have done in the past years. So we're trying to combine, different type of data and also multidisciplinary models and tools, to digitalize the building environment, and also to automate the characterization of the building the stocks, to inform circular construction and low carbon transition of cities. Like I showed this telescope and microscope perspective, so we harness multidisciplinary tools and data, some from very classic civil engineering and architectural knowledge, like what kind of materials we will use for rooftops and floors and so on. But also new types of data like remote sensing, but also LiDAR data, even like historical maps, as I show here. If we want to understand the dynamics for such urban building environment stock development, we put this kind of information together, and this way we could provide a spatial and temporal dynamics of building environment stocks and both building and city and national and global levels. And this, to our point of view, provides or actually helps to achieve the triple wins among digitalization, circular economy, and climate change mitigation discussion. Because as I mentioned, there has already a momentum in the construction sector, in the urban big geodata analysis field, for digitalization. Well, on the other hand, on the quantitative accessibility assessment side, we are aiming for also higher resolution to support circular economy and climate change mitigation in cities. So what I will do in the next few minutes is to quickly give a few examples, how we can do that and why we do that. So the first type of example is gridded global mapping of built environment stocks, because we could, of course, derive such global mapping on a national scale or global scale, but normally we do not have a very high resolution. So here is just one way we try to approximate the building environment stock distribution by combining the lifetime night data with the national scale urban building environment stocks. So by developing some sort of regression for major construction materials for different regions, we can develop such a correlation and apply that to downscale the national level stocks and 1 kilometer by 1 kilometer grid level. And this can actually help to understand our patterns of urbanization at a refined level. So this result figure is visualized in an RGB style. So we have red color, green color, and blue color represent the values of gridded building environment stocks for 1992, 2000, and 2008 respectively. So that means, when you have the 3 years with very high values, putting them together, we will get like really strong or dark white, right? So color. As you can see, this is for North America, the Great Lakes area, and this is for Europe and North Africa, and this is for East Asia, and this is for the Middle East. So if the color shows correctly on your screen, you can see, as I said already, you know, in the Great Lakes area, we only see very, you know, bright white color. So that means, of course, after 1992, the stocks are all at high level and do not change that much. And this is, of course, very straightforward because cities in these areas, including Japan, actually have already completed this major urbanization process, you know, with proper buildings, infrastructure, and so on. But if you look at like East Asia, you will see South Korea, or first of all, you can't really see North Korea here, but you can see South Korea is a little bit greenish. So this means, you know, the values in 2000 still increases and actually hide, you know, the 1992 value. So this, of course, we know after the 1988 Olympics, the Korean economy has still shown increase pattern. And in East China, the coastal Chinese provinces and cities, you will see very blue colors. That means the value for 2008 is still very high. Or even if you zoom in for the Middle East, you will see some red spots. I don't know if you can, not my mouse, but like, you know, the red spots on the map here. These spots means, you know, in these graded cells, you know, or cities, we have actually, you know, a loss of built environment stocks. I mean, this was, you know, primarily due to, you know, the wars and, you know, other kind of conflicts. We could also combine such specialized analytical way with other urban built environment stocks methods like, you know, material flow analysis and also different types of data to provide a specialized urban stocks mapping. So, of course, we have to rely on data like, you know, the big data mining, you know, for some parameters, you know, we do not have. For example, in Chinese cities, normally we do not have the year of construction for many buildings and even for the types of buildings. So we have done quite a few case studies, you know, along this line. Here, just very quickly, example for Shanghai. So here you see material inflow, stock, and outflow between 2 years, 1980 and 2010. So for stocks, you know, clearly see after the open and reform policy, you know, the past 30, 40 years have resulted in a fast increase of stock, you know, across the entire city, and of course also in the city center. But if you look at outflow, and this, in other words, means, you know, the construction demolition waste, they gradually expand, you know, to the outer side of the city, and also for resource demand. So such kind of specialized mapping can enable, you know, more smart urban resource waste and environmental management. For example, we can develop or we can optimize the logistics for the construction demolition waste transportation, collection, and eventually management. You know, here are two other examples for Benin and Beijing. So here you can even see, you know, the CBD of Beijing, and also, of course, you know, within the second ring, we have Forbidden City, and, you know, in other lower rise building, you know, we have a kind of a lower stock. So such map, this is for Benin, we have shown more raster data, but you can also see the same. So it provides a physical basis in a specialized way, you know, for you know, discussion around circular economy and climate change mitigation. So this is a case for Odense, so more a European city. So we also harness data from, you know, civil engineering. So we really dig into the architectural design, you know, in the historical documents, and we can put together and provide such a mapping, not only for, you know, all the materials, but for different types of materials. You know, are we talking about steel or concrete or timber? Of course, there will be a difference, right? Even, you know, per building and per wall. Here's for a few buildings in the downtown, and we see how concrete and clay bricks are distributed, in different walls or buildings in the downtown. When we combine such kind of mapping with also historical maps and knowledge, we could even develop like a longer time series, building environment stocks mapping, so that we can understand how the city has developed. For example, here, a case for Odense again, how it developed since 1810, and we have been accumulating, each piece of a brick, in different buildings, across the city, and for different services and different functions, and in different, urban zones. So such kind of mapping actually serve also as a physical platform for example, discussion around circular economy and climate change mitigation. It also, when we do this for multiple cities or even all the world cities in the history, so we can also understand, for example, the specialized patterns for urban growth. We had, of course, this kind of understanding from a two-dimension perspective in geography or urban geography, for example. When we talk about land use change, when we talk about population, dynamics, there is already a lot of research. But from a three-dimension point of view, how we have been accumulating resource, it's also very important. And I argue this is also a third perspective, to understand urbanization. So here is just I don't have time to go through details, but we have modeled, the development of 50 plus Chinese cities, so we can look at like this kind of a spatial pattern, and to look at how different cities vary in terms of their stock accumulation. So is it like a monocentric concentration to a multicentric dispersion to a multicentric concentration? And of course, this kind of understanding can support a discussion, as I mentioned at the beginning, around the role of urban planning for the circular and low carbon transition. I think this figure might be familiar to some of you. It basically shows the per 1,000 person or per capita car ownership against urban density. So if you think about the cities here, in East Asia, in extreme case like Hong Kong or Singapore, they have a very high density in terms of people per square meter, but they have much lower, car ownership, either because of the, development of the public transport, but also because of this limited land, right? We actually have very similar patterns, for other infrastructure, and this is of course only on the city scale. So we only look at panel data for all cities, not yet on the spatialized level as we showed before, but we can explore that kind of patterns with the digitalized urban building environment, as I showed before. And also such building environment stock characterization can help provide a more complete picture for the urban emission accounting. I think you have already heard about a keynote from Professor Mi around greenhouse gas emission accounting for cities. So here we plot these operational emissions. Why we call it operational emissions, this basically means when we run the city. So that will be the building energy demand, the transport energy demand, the industrial demand in the city, right? So we can look at the emissions from different sectors, from service, from household. So for example, big cities like Shanghai, Tianjin, Shenzhen, and Beijing, of course, they have higher emissions because more people live there and more people drive and so on. But we also plot this against this so-called carbon replacement value of urban built environment. So this is a simple proxy of emission cost of a city development. So this is calculated by estimating the emissions needed for reconstructing all the built environment, using today's technology and materials. So that means if we build, changing from scratch, using today's materials and technology, what would be the emission cost? So this is a kind of a proxy like, we use for the real estate market, right? So you will see city like Tangshan, so they have not very high, carbon replacement value, because it's kind of a small city with not so many built environment stocks, but it has a very high operational emissions, because this is we all know it's an industrial city with a high steel production capacity, right? So this kind of dimension perspective can help us understand the emissions not only in the operation of the city, but also in the construction of the city. And such understanding, of course, will be important for developing new cities in the West, but also to inform the circular and low carbon transition of cities in the global South. We can use such understanding, for urban mining and also circular economy, of course, like, here, just like how we can start from this urban layout and stock prospecting to the resource characterization in terms of grid and tonnage, pretty much like, we do in geology, right? In geology, we characterize, we quantify, reserve underground. And now we are characterizing urban mines above ground in terms of their quantity, quality, location, and also temporal dynamics. So such knowledge actually has been used. This is a case from some of our colleagues in Linköping, Sweden. So they have actually already been using such knowledge to support industry, for urban mining in the Linköping city. So that's all. I think I just exactly used 40 minutes. So I will not read all the take-home message, but yeah. So what I want to elaborate, or again, as I put in the title, when we digitalize urban building environment stocks using data and tools from different disciplines, it can provide a physical basis, to inform our circular economy and climate change mitigation discussion in cities. With that, I would like to thank you all for your attention. And if you have questions, I would be happy to answer. Okay, back to you, moderator.
Thank you, Professor Liu. Thank you giving us so insightful and informative Is there any questions from our audience? You could turn on your microphone, or you could type on the chat room in the Zoom. Yeah, so maybe I could ask a question. So I think Professor Liu has did a like a really big and large scope analysis about the stock of the city urban build. So may I ask that from I saw that you have this kind of graded levels evaluation. So may I ask, like at present, what kind of graded value are you in right now? Like for example, 0.5 multiple 0.5, or even like a smaller version?
Yeah. Thank you for the question. I think this of course depends a little bit on the purpose. In different studies I presented, of course, we were using different resolution. In general, of course, the more refined, the better. But of course, the more refined, the more data you need, right? So when we look at some sort of patterns, either within a country or globally, so we normally use data that are globally available. So that means sometimes we cannot really zoom in. Concretely, like one example I showed for the nighttime night imageries, because of this kind of material effect, of using the nighttime night, so we cannot actually provide very high resolution, mapping. But if we combine that with other bottom-up data, from, for example, any travel modes or high resolution remote sensing and so on, of course we can still improve that even to 100-meter level. think for the Danish case I showed, we are actually on the 100-meter by 100-meter level. As I said, also ideally, such resolution should be used for some sort of logistic mapping. We have been working together with, for example, some waste company, especially the demolition waste management company. So they were also interested in using some sort of tools or such resolution to support their business. In this case, of course, they want even higher resolution, because they can use not only for logistic optimization but also for really different types of circular economy strategies. One example is reuse, right? So when we want to reuse maybe some sort of building components in the new construction, so we have to look at like where we have them, how much we have them around this neighborhood or maybe across this city. So it doesn't really make that much sense for a piece of building component to be transported like 20,000 kilometers to be used, right? So just like to put it simple, I think this depends a bit on the purpose, and the most refined level we are now working on is 100-meter by 100-meter.
Okay, thank you so much. And I noticed that in one of your slides, you mentioned that there is, I think it's a relevant like graph is about the urbanization and the cement stock growth. And you have mentioned about the different countries and about their urbanization rate and the cement stock usage. So some of the country, as I remember, they have already has a like from a U shape to the G shape. So they have like paused the increase and the decreasing, like has the turning point about the decreasing trend. So yeah, exactly this one. So is there like a any kind of result about following the roadmap to China's carbon neutrality, to what kind of extents about our urbanization rate we will have gonna reach the same turning down trend about the cement stock in China?
Yeah, I think this is a very good question. As I mentioned, so I mean, even among the industrialized countries, you will see they also look a bit different. For example, Italy, it has much higher, per capita cement stock comparing to the other industrialized countries. One reason we assume is that there are a lot of buildings, made of concrete, for this kind of heritage building when they have to reconstruct it, based on like more traditional styles. So they have been using like more and more cement. But of course, this is our assumption. Without a more bottom-up understanding, it's a bit difficult to compare. But if we talk about China, as you were asking, I think definitely, well, urbanization will continue, right? So I think this is a bit old data. This is until in 2009. So we were talking about urbanization rate still lower than 60%. Now I think it's higher already. We will go to, if not 80%, maybe 75, whatever percent, in the next decades. And that means we will need more buildings and infrastructure in the cities in the West. So we will still increase like, this kind of stock curve. When it will saturate or level off, or even like, as you said, like, maybe decline, this is a bit difficult to predict. But, as I also put like in a slide later, so it matters a lot for the urban design. So how are we constructing our city, right? So this really links to discussion around regional and urban planning, and also transport planning and so on. So that's also our motivation, but also argument. This resource perspective should be added, into the urban planning and architect, design discipline, so that we can work together for at least this circular economy, and also, of course, or dematerialization and climate change mitigation issue. So for cement specifically, of course, when we use that much cement, no matter if we talk about China or global, this cement production produce roughly 7% of the total emissions. So that's actually quite a lot, much larger than many other sectors. So this is something we have to handle. As I said, we will not run out of cement resource in China, but we may face a constraint for how much we can emit out of the cement we need for urbanization. So we do need to avoid this, as I put, like obese person here. So sometimes it's not too good to be too heavy.
Thank you so much. I'm not very I'm not an expert about architecture or building, but I'm curious that does the development of the new material of like architecture or building or even like a smart building, we're gonna like replace some of the stock of cement in the future, or
Yeah, I think,
will that be helpful for like to at some extent to reduce some like carbon dioxide?
yeah, for sure. I mean, spatial planning I mentioned already, but you are very right. Material substitution, that's also a very, very important strategy. I mean, there has been a lot of discussion around use of timber, even for high-rise building, right? So, but also other organic materials, for the construction materials. So that's definitely a way to go as well.
Thank you. So we have some like audience, so we really encourage the participants from our audience. So is there anyone have the questions? And you should grab this great opportunity to have the communication with such a great professor. So it might be a little bit shy. Yeah.
Yeah, no problem.
Yeah.
If you have any questions, I have an email also, just I put on the slide, so you're welcome to contact and we can discuss bilaterally as well.
Okay. Thank you very much. Thank you, Professor Liu,
thank you.
for your
thank you. It's
very
my pleasure.
insightful presentation. Thank you.
Okay, thank you for having me.
Okay.
Yeah.
Thank
Bye.
you. Bye.